Hello and welcome to Cambridge, Massachusetts. Tonight I'm with Marta Gonzalez. Marta is a professor of civil and environmental engineering here at MIT, and Marta has been working in a variety of very interesting things. Among some of these things, I know that you're very well known for some work that you've done on human mobility using data on mobile phones. So I would like to start asking you a little bit, what was that work about and what were the type of things that you found out in that research?
Well, yes, I can tell you how I start being interested in working with that kind of data. And all starts in my PhD thesis. My PhD thesis was contact networks of mobile agents, and we used to see how that, something spread in the network according to the contact rate and how movement and interaction changes. Then the thing is that usually, as a physicist, we can simulate movement of agents, and the typical thing to use is a gas, ideal gas. Then we were changing the interactions, the network would change, but it was pretty hard to make that this gas movement resemble human mobility. And then, since PhD years, I was thinking it was very complex programming tools to have the snapshots, all the properties of the network in time, but we did not have an idea how to model each single particle. Right. And that definitely drove me into the need to go to the place in which they had the data about human movement.
So you were asking yourselves about the way that people interact, but before starting working with data, you had the problem that you had to base this work on assumptions.
Yes, yeah. Yes.
And now when you got your hands on the data, what type of things did you started to look at?
Exactly. Then when I finally got the hands into the data, then came the problems. The data was so huge that all the programs were breaking, and it was very hard to, it was like an ocean of information. It was hard to start seeing what we would do, what we would see in principle. But, well, actually, what we start doing is comparing, using the traditional tools to characterize trajectories. And the usual trajectories we characterize in the community are the random walk or the levy flight. So there are some tools to characterize the characteristic properties of the ensemble or of the groups of walkers. For example, we can start measuring what is the average distance of travel from the origin as time evolves, how is the average distance of each of the walkers, how it evolves in time. And usually the math gives you some particular exponents of characteristics that you expect from the system. And then what we start doing is creating the groups of trajectories of people and measuring the same things that were measured in other known trajectories. And we start seeing that nothing looked like as was seen before with the random walkers, for example.
So what was the main difference between what people have observed and what you observed?
Yes, one of the interesting things from the system was the heterogeneity, in the sense that usually we were used to model things with some parameters, and then you have a group of walkers that all behave the same way. And in the human groups, we don't have that. That means we have that some people travel much shorter distance and some others travel a much further away distance, and that changed completely the distribution, for example, of distance of travels.
So it would be okay to say maybe that the average person did not exist when you looked at the data.
Exactly.
That there were people that were moving over big distances, and there were people that were moving mainly over short distances, but the average person did not make much sense.
Yes.
And what's the implication of having a world in which actually there's no average person, but there's large levels of heterogeneity?
The implications is that the models are had to be built, basically. So what it has been used to model how people was moving, or for example, how diseases were spreading, were based on the traditional models in which we can measure everything like a continuous time random walk, for example. Then the spreading dynamics would be completely different in this new scenario.
So all the modeling that we have built on the way that people were moving basically was wrong, was having assumptions that were a little bit too strong to satisfy our reality.
Were strong assumptions, and the main reason for that is that it's like I came to this research at the right moment. And the reason for the wrong assumptions is that never we were able to measure mobility at a country scale for long periods of observation.
So you got data at that time on mobile phone records.
Correct.
But I know that you have been working more recently in other ways of capturing the mobility of people. What are other ways that actually you can capture the mobility of individuals or of a population?
Nowadays, in the information age, pretty much many things get saved, and then all those records that get saved are sensors. You can think in transactions with your credit card, they are saved, and through that we can also capture measurements of how people is moving. Or every time you log in your, for example, with your email account, the IP has coordinates associated with it. Then you can track through that. And particularly, I've been studying smart cards from the subway. Then we know how people every day, for example, in London, how they commute and which stations they visit in the city. And we start characterizing the trajectories, the properties of the trajectories in London. And there are surprising similarities with the statistics that we observe in the mobile phone. So it doesn't matter much which sensor you are using, you get the signal or the law that it belongs from the movement of people. Then we observe the same heterogeneities or...
So you're able to use all of these different ways of trying to understand or trying to map how people actually move. And now that you know how people move, what type of applications can you build? How can you help society with that information?
So there are several applications in which they would benefit from a detailed mobility model. One area of collaboration is the epidemic spreading. In that case, you need to be very careful of which disease you are modeling, and the epidemic part require a set of knowledge itself, and careful dedication to that. So in that case, for the epidemic spreading, that is definitely something of interest. Usually, I am in charge of the mobility part, and some collaborators do the epidemic spreading. That would be a collaboration. I myself, I've been concentrated in detecting how people interact with space, and I am particularly interested in cities, because cities is a complex system in which you have different kind of tribes or different kind of behaviors, and there are a lot of challenges in that area. Nowadays that cities are exploding with people, and we would like to design better cities, is a perfect area to do research on. So I've been trying to see how, using the same amount of data, to see how people select different destinations inside the city. And some recent research I've been doing is not only exploring the distance or some statistical measurements of how the trajectories of, not looking anymore the trajectories in abstract, comparing with random walks, but actually capturing from the data the origin, the destination, and making the matching, what is called map matching in the streets.
Okay.
Now, every certain time, we know when people move from one place to the other, you can actually, it's easy algorithms to know which streets they took. And we can do that with 500,000 users, mobile phone users, or a particular city in a particular hour. And that gives us a lot of power to have a very cheap way to see how people is using the city in real time.
So then I assume that this has amazing implications for transportation, for instance. What are the things that people are thinking about on the way that we can use this to improve our transportation systems, to improve our road infrastructure? I assume that you participate in circles where this conversation is very frequent, and I'm wondering what type of things people are thinking about a future in which this data is going to be enabling new ways of creating better transportation systems and better infrastructure. Can you tell me a little bit about that?
Yes, yes, I've been amazed by the fact that still the way how people plan the demand, the transportation demand of a city is based on travel diary surveys. So, and that surveys are still done nowadays. For example, I can tell you the city of Chicago made one recently in which they can ask usually 1% of the population. Then we're talking about 30,000 people being interviewed, and in which they tell you exactly what are their activities in a daily basis. Then you have the information of the travel and activity demands of people, 1% of the population, only 24 hours. And that is all what we have to model the origin and destination of the entire city of Chicago.
So the transportation system basically is being built using very little information about the actual movement of people.
Yes. And then here we come with the mobile phones, and what I have been focusing over and over is that you can use the location-aware data, name it, it can be smart cars integrated with smartphones, integrated with not smartphones, all the data that tells you, coordinates resolutions about where people is. We are trying to validate and compare how those things are really a way to get the same information of the surveys and better.
Oh, okay. And then when you start doing this, when you start showing this map, is there people that actually is interested on starting to use this? What is the interest that you have been able to gather, or you and the community have been able to gather from?
I can tell you the recent applications, and it has been on trying to reduce congestion in the city. For example, what we did is to map the trajectories of 500,000 mobile phone users in the Bay Area and in the Boston area. And the first thing, we have to develop the methodology, because if I told you that still they are using the survey, and there we come to say, okay, stop using the survey, we can use the mobile phone data. The first thing we have to do is to validate. Then we show, in fact, our estimate of volumes of people traveling in the streets at a particular time of the day was the same estimate as measured by other sensors, like, for example, GPS. Then a GPS, usually we have, for example, taxis in the Bay Area have a GPS device, and with that you can know the velocity of the taxis in, name it, 1,000 streets in San Francisco. The advantage of having the mobile phones is that you have the volume, that is, you are knowing how many people is going from where to where. Then, for a particular street, you know all the mobile phone users that pass through there. Then what we start doing, and here we go with the application, is given a street, where the mobile phone users that went through that, where do they live? And then we call these places major driver sources, and then we were connecting the congestion of a street with its own major driver sources. It's like a network hidden in this scene. Then you can think in the local road of your neighborhood, it may be congested, but it's only used by you. But you can think about Mass Ave, perhaps, is used by how many driver sources in the Boston area. Then we start doing this matching, or this mapping, or this intrinsic network, and then we discovered we also made the statistic of volume over capacity. A street is congested if the volume exceeds its capacity. Then we capture all those streets in each city that has VOC, volume over capacity, greater than 1, and then we also could link these streets with the neighborhoods that were generating that traffic in the first place. Then we could do a rank, sort of saying, what are the neighborhoods that are most affected by congestion, and then we could design a target strategy to reduce vehicle usage exactly in those neighborhoods. So this is an amount of information that if you are working with only 30,000 users, you can try to upscale the travel demand, but you are never going to get this kind of detailed information.
So in a way, this is another example in which having more information allows you to do things that you were not able to do with the information that you had previously. It's like the true definition of technology, a technology that is opening new possibilities that we were blind to before. Now, I want to change the topic a little bit, and I want to ask you about another area of research that I know that you have been working on, which is recently you published a paper on the diffusion of Twitter. And I know that a lot of people actually participate and are interested in this social platform. And I would like us, if you could please tell us a little bit about, what was that paper about? What did you learn about the way that Twitter diffused?
Yes. Let me tell you a little bit about why I started. Despite I was having a lot of work with the movement and so on, why we took that approach. And the thing is that since I was working with the mobile phone data, behind the scenes, we were trying also to understand how things diffuse in the call graph. So we were studying not only the trajectories of people, but we tried that, okay, let's see if the mobile phone company have a new product, how it diffuses, and if it becomes viral. And that thing, like how an idea or a product becomes viral, is a very important thing. The reality is that while I was working with the mobile phone data in the call graph, not many things become viral. And in fact, most of the things in the internet nowadays do not become viral. And then it happened to come Mia Chang to my office and told me, I am working in Twitter, and yes, good. And she was doing what most of people are doing right now in Twitter, that is how ideas or hashtags spread right now. But she told me that she has been crawling Twitter since the origin of Twitter. Oh. And then I saw the opportunity there, because she came here with the same product, one of the few cases that really became viral. So she had been counting the users. So she knew where the users were when they signed up for Twitter, and she has a story when they were 10 up to 3.5 million in the US. So how Twitter was born. And okay, here we wanted to see how it would do it. And because I've been trying to concentrate in the spatio-temporal phenomena in general, I wanted to see how it happened within a city. So how is the process that it takes, how something becomes viral in space and time. And then, we developed the research, and we discovered some things. And some of the things that we discovered is that despite we knew what was the composition of the cities. So we had there the 400 cities in the US in which they had at least 1,000 Twitter users to have good statistics. So we saw that some cities has many early adopters. You can think like Ann Arbor, Michigan. They have many early adopters, and it's related to a location of a university. We have Somerville, also like early adopters, and we have other cities that didn't adopt so early. So there we had it. We had the composition of every city, and we can do the typical spreading dynamic modeling with the right composition of each city, and see if we could predict when each city adopted. And then we discovered that the composition was not enough, and we needed to introduce two ingredients, basically, in the social network. One was that the way you select your friends has to do with homophily and closeness. So it had a spatial component and an homophily component, and by homophily means that you have more probability that early adopters are connected with early adopters. And putting these two ingredients, you run the model and you run it many times, and you get the average in which the average week when one city adopted, and we could predict all the process, from the ones that adopted very early and the ones that adopted later. So in that sense, we learned that part, and also the way media is introduced into the adoption process also had to be different as it was introduced in some previous models, and that is that it's not true that the media just start being more popular the more people has it. They are sometimes hyper influential. Not all the media is the same, basically. And then you have to target some random events in which sometimes the media is much more.
So the media would be like an external driving force that sometimes it is exogenous to the diffusion process, but it's necessary to explain the dynamics that you observed.
Yes, and that was also introduced in previous models, but it was like a linear term, and we needed linear term plus random chunks. So this that sometimes you have a media event that has a lot of influence.
So now you could say also that from your study you could go back and find which are the cities that are early adopters, and in the future, if there are other technologies that would be similar, you could also even identify which are the places where this would be adopted first.
Definitely, and in fact we provide in our webpage the label of each of the cities.
Like a ranking of how early adopters they are.
Yes, because that is what I think.
And does it relate to any more traditional or simple characteristics like age or education? What are there any demographic covariates that correspond to being an early adopter or not?
I think we didn't really explore that, but I think it may be related to age in the case of Twitter, definitely. It had to do with the location of big universities.
Okay. Well, on Facebook also, like a lot of people know that in the beginning was a network that you had to have a .edu email in order to be able to participate, long time ago.
Right.
Yeah, and then they expanded to the rest of the world. So now that we know a little bit more about what you have been doing and what your lab has been doing, I would like to get to know a little bit better. I would like to get to know you a little bit better, actually. So with that in mind, I would like to start, we all know that now you're a professor at MIT, but obviously you were not born a professor at MIT. There must have been a trajectory that took you, from where you grew up to there. And I would like to go relatively quickly, through your life, so we can learn about your trajectory and how do you get from where you started to where you're now. So can we start from where did you grow up?
Yes, I grew up, I was born in Venezuela, and I was born in a small town where the oil company, many oil companies are, and my father was working in the oil company, and then I was born there. It's a town called Lagunillas.
Lagunillas. And then in Lagunillas, you went to school and everything. When did you start to become interested in science? Was it early on? Did you have other interests growing up?
Since high school, I was fascinated by physics, and I remember one of my high school teachers telling me that I should study physics, but that is a hard decision because you never, when you are a young high school student, you never know which kind of job you can end up having if you study physics.
Especially in a country like...
Especially in a country like Venezuela. Then I remember being in the first year of university, and I thought I wanted to study physics, but I chose chemistry, pure chemistry, okay. Because I thought, well, if I study chemistry, I can work in oil. So we are in the oil industry. Then that made sense. But when I was seeing quantum mechanics, and I knew that studying chemistry, I was going to miss the real explanations.
Okay.
I could not take the quantum physics, and I really was not what I wanted to learn. I remember once walking in the garden of my university, and I said, I don't mind if I'm going to be starving later. I want to study this now.
Okay.
And I went and changed, and I started studying physics, and I enjoy it all the way.
The university was not in Lagunillas? Or?
No. It was in Caracas. When I was 15 years old, I moved to Caracas. The whole family moved to Caracas,
and then after you graduated from the university, so you graduated with an undergrad in physics.
Yes.
And what did you do next?
Then I said, now I'm going to start. Even to teach at the university, you need a PhD. And I wanted to, so the question is, where am I going to work? Because I realized that not many companies do research there. And then came the usual move. I started looking for where is a place I can work on and continue doing research. And that was, in fact, no surprise, in the oil industry. And I started doing a master in which I could do an internship. And the master was going to be in transport in porous media, that in statistical physics we do that, and then I focused my research on that and started doing research. And in fact, I got after 1 year of research there, I got a position as a researcher, so I could have done my entire career focusing to the oil research.
But then you didn't, so
I didn't.
How did that change?
Then it happened that it was a great group there, and it was a group that did statistical physics, and my advisor sent me to present a poster in the StatPhys, which is the big meeting in which all the people that do statistical physics meet. And then I started looking the community, the papers. There were people working in granular material, there were people working in water, and it's very funny because I saw people that was doing, I saw especially women researchers that work from Italy, and they were presenting their results and they were finishing their PhD, and I was like, wow, I want to do that. And I asked one of them, what are you going to do next? And she told me, well, I'm going to do a postdoc. And I, honestly, this is true, a postdoc. Oh my God, I haven't done my PhD. It's something such cool thing, a postdoc. Then I really, for me, that was a new universe, and I really wanted to go for it. And I wanted to have the freedom to do research in anything we were interested, and that didn't have to be necessarily oil or something like was a constraint. I wanted to go for a free
freedom, and oil.
I wanted
the oil
that.
industry did not give you exactly that creative
Yes.
freedom that you were looking for.
Yes, and then I came back, and it was very funny because I remember that was July when the StatPhys that was in Mexico. I came back and I started my new mission, despite I have the very good job, being a physicist, having a job in the research institute for oil is great. It's a great job. You could have career. They would give me a scholarship to study oil in detail, but I didn't want anything of that. And I started looking for which scholarships are in the country to do basic research abroad. And I started calling and looking in the internet, everything. And it appeared a great program that is the DAAD program, that is the exchange program of Germany. And they select 4 people in the country. And I apply, and they interview me, and I think I convinced them that it's not that I don't have the job, it's not that I don't have opportunities, I really want to do this. And I got a scholarship and went to Germany.
And then you went, and then in Germany, who did you work? What city did you land in? Well, how was that part?
Stuttgart, to work in Stuttgart University, and I started, in fact, being in the network that do statistical physics, that is a community of people that do related research with chaos, fractals, and later complex network. And I started working with, once I got the scholarship, I decided where I would go. And I wanted to work with Hans Hermann, that belongs to our community, and I started there. And I remember Hans at the beginning told me, yeah, there are some, he tried to give me a topic that had to do with sand, deposition, because for the oil industry, I said, no. I don't want. I want something, new, free, because it's basic research, so it doesn't have to be oil.
So that's when you move from the chemistry of atoms to the chemistry of people.
Right, and then Hans gave me the topic that was the newest at that time, and the one with the major risks. And he gave me, okay, then I start working with complex networks. This was in 2003, and the big papers on complex networks were 2000, 2001. So it was very new and fascinating because everything was to be done, and it was crazy because only 3 years later, there were so many publications already that I really have to read a lot. And in my group, when I started in Hans' group, I was the only person doing networks. That also was a challenge because many of the guys of the lab didn't have an idea why I was working with social networks if we are physicists. I had to explain, long explanation, why I was doing a PhD in physics working with social networks.
And then how did you go from Stuttgart to the United States and eventually to MIT?
Okay, yes. Then, well, I developed some work with the contact network of mobile agents, and I needed to go, my next step was to see where I could measure these real mobile agents that had to do with real data. And most of the groups that were working with real data were here in the US. And particularly, I had the fortune that I was interviewed by Laszlo Barabashi, who is one of the pioneers in the area. And I had the fortune, I was hired as a postdoc, and no doubt I just moved to continue doing this research with one of the creators of the area.
And then how did you go from being a postdoc at the Barabashi lab to being a professor at MIT?
Well, then it has to do with being in the right place in the right time. And the thing is, it all gets connected to what we were talking before, is that the way people model how how is it modeled? How people move in the city, it relies on surveys. And in the Laszlo's group, we were doing analyzing mobile phone data and extracting laws of movement at a country scale, at massive scale. And that was a piece that is very important into the curriculum of transportation models, transportation engineering, that is in the Department of Civil and Environmental Engineering right now. So when I had this research and publications analyzing massive amount of mobile phone data, and exactly at the time I was looking for a job, they had an opening in transportation research. And this kind of research was perfect for that position, and I start, and that's what I have been doing.
That's great. That's a wonderful story. You know, it's a wonderful story how you go from Lagunillas, an oil industry town, to become a social chemist. So thank you very much, Marta, for joining us tonight. You know, it was a pleasure having you.
It's my pleasure. Thanks.
Thank you.